Hey everybody. So I thought I'd do a slightly more complex projectile problem today where we launch a projectile up an incline, right? And the incline is a certain number of degrees deviated from the ground, and the launch itself is a certain number of degrees deviated from the actual incline, right? So you can think of this like we're launching a projectile from like a cannon or something like up a hill. And we're asked to find how far does the projectile actually move along this incline, right? Or our distance d right here, okay? So the actual details of the problem is a projectile is launched along an inclined plane at an initial velocity of 70 meters per second, okay? The incline is elevated 15 degrees above the ground. That would be this angle right here. And the launch angle, right, is 20 degrees above the incline. That would be this angle. Okay, so you can already see, right, the total, right, these are adjacent angles, so we can absolutely add them, right? And so the launch angle, it's actually, right, 35 degrees, right, above the actual ground, okay? So again, we're asked to calculate how far along the incline will the projectile actually travel. Okay, so the challenging thing about this is that we really don't know what the change in y is going to be. We really don't know what the vertical displacement is going to be. And as you probably maybe recall from less complex projectile problems, that's usually how we determine the time, right, that this object actually spends in the air. By first determining how much time it spends in the y-axis, we can also know how much time it spends in the x-axis. But if we don't actually know how far it moves, right, from ground to landing, right, because these are two different elevations, and one of the elevations is unknown, then finding the time can be challenging. Now, if we did know that displacement, let me get my draw tool. Okay, if you were like launching from like a platform of a known height to another platform of another known height, right, then you could simply use something like this, so delta y, right, equals v naught in the y, right, times t, the time spent in the air, right, minus 1/2 g t squared. Right, so if you had a value for everything but t, right, then we could basically set this to 0, right? I could just subtract delta y from both sides and put this into the quadratic formula, essentially, right? And then solve for t. And you would get 2 t's, right? And that's not some sort of mathematical abnormality. You'd actually have the object passing, right, a particular height, whatever that height is, twice, right? Once going up and then once going down, coming back down again to land. Okay, but we don't know delta y. So we have to use this equation a little bit differently. We have to do a little bit of clever algebra to find our delta y, and then use that to find t, and then use t to calculate how far it moves horizontally. And then once we know, and you can see this is just a right triangle, once we know x and we know y, then d should very obviously equal formula for the hypotenuse of a right triangle, which would be square root of its legs squared and added to one another. Right? Square root of x squared plus y squared. So most of this problem we're going to spend figuring out y, right? And then figuring out x should be a fairly simple task, and then we can just place them into the Pythagorean theorem, which is what this is, and we can calculate d, okay? So I'm going to go down here, and we have the specifics of the problem down here just without the image, and I'm going to do exactly that, okay? So first what I'm going to do is I'm going to calculate the time, right, or get an equation for t, right, or for y rather, right, and then I'm going to get an equation for x, and we'll try to see if we can integrate them, okay? So stay organized here. In the y-axis, okay? So what I'm doing here is I'm going to get two different equations for y. I'm going to set them equal to each other, right? And then I'm going to use them to solve for t, okay? That'll become more apparent as we go on. So once again, right, y, to break apart the delta, y is equal to y naught, right, plus v naught in the y multiplied by t minus 1/2 g t squared. Okay. So what we can know right away is that y naught is simply 0. I mean, we're just starting off, right, basically at the ground. Okay, and the incline deviates from the ground, but where we're starting off is just sort of like this vertex that the launch angle has with the ground itself. Okay, so this is 0. Okay, and cancel that out. Okay, we don't know what the final y is going to be, and we can just turn this into numbers if that makes more sense to you. And so in order to do that, we're going to have to decompose our 70 meters per second into the v naught y. Okay, so let's do that. So v naught in the y is going to equal 70 meters per second multiplied by the sine of the angle, right, that deviates from this horizontal component right here, okay? And the angle that it deviates from them will be the sum of these two angles, these two adjacent angles, right? Share this vertex, and that'll be 35 degrees since this is 15, right, and this is 20. Okay, so multiplied by the sine theta, which is simply 35 degrees. While we're at it, right, we can go ahead and get our initial velocity in the x-axis as well. Okay, so v naught x is also going to equal 70 meters per second. Multiplied by now, because we're dealing with the x-axis, right? This isn't always the case to use the cosine for x-axis, but it is in this case. Multiplied by the cosine of theta, which is also, again, 35 degrees, okay? So let's get out the calculator. Okay, let's see what that equals. So 70 times sine of 35, okay, equal to 40.15 meters per second. And then 70 times the cosine of 35 equal to 57 34 meters per second. Okay, now that that's done, okay, we can plug some numbers into this, and basically what we can do is we can get an equation for what y equals. Okay, that's not going to solve our problem just yet. That's not going to allow us to just quickly calculate y because we don't know what y is and we don't know what t is. But we're going to find, right, that once we solve for y, right, we basically already have, right, in a sense, right, if we knew t, then we could solve for y, right, then we can know what this vertical component was, okay. So let's simplify this a little bit, okay, just plug some numbers into it rather. So So y is going to be equal to, okay, v naught y, which is 40.15, okay, times t, minus 1/2 g, g is 9.8 meters per second, so 1/2 of that is 4.9. So minus 4.9 times t squared. So you can see that if you knew what t was, you could know what y was, okay? So what we need is another equation for y, okay? So that we can set those equations equal to each other and then just do the necessary algebra to solve for t. Okay? So let's get another equation for y, okay? So let's talk about the x-axis for a moment. The x, okay? We know, right, that x, this horizontal distance right here, is going to be equal to whatever the initial velocity in the x-axis is, multiplied by time. That's because in these sorts of problems, especially in like basic physics, we really just kind of assume that there's a constant acceleration. So remember, g in the vertical is sort of taking the place of a, right? So on the horizontal, this would just be a. But if if there's a constant, right, velocity, right, in that x-axis, then a would basically be 0. So you'll lose this entire term, and you basically just end up with this, right? You just end up with v naught in the x for our example over here, right, times t, okay? And this would be x as well. So x just simply equals v naught x times t, okay? How fast we're going in the x-axis initially, multiplied by how much time actually goes by, okay? All right, so, okay, but who cares, right? How does this help us? We need an equation for y, right? Well, what I also know, right, is that the tangent of theta, okay, in a right triangle is equal to the opposite side, right, with respect to that angle that we're talking about, whatever theta actually is, right? The opposite divided by the adjacent. Okay. So let's look at this. If this is the right triangle that we're using for this particular definition, right, this would be the angle, this would be the theta that we're talking about, right? Deviation between this hypotenuse right here and this horizontal component, right? The x would be the adjacent, right? The thing that actually comes into contact with this angle here that shares a vertex with the side that's actually deviating. And this would be the opposite, right? The y. So what this essentially translates to is the tangent of this angle is going to be equal to, let me erase this. Well, I'll leave it there. It's going to be equal to y over x, right? Okay. Don't we already have a definition for x right here? Couldn't we just place these variables into the position of x, thereby substituting, right? And solve it for y. Right? So what I'm going to do here is I'm going to multiply x, right, on both sides. And this cancels out. And we have now another equation for y, right? Y is going to equal tangent of theta, and in this case, it's just we're not going to add these anymore because we're just dealing with this particular right triangle, right? The tangent of, what is it, 15 degrees, okay? Tangent of 15 degrees, okay, multiplied by x, which we've already agreed is v naught x t. That's okay. All right. So let me plug some numbers into here. Simplify this as much as possible. V naught x, we already know, is 57.34 meters per second. Right? Tangent of 15 is some number, right? And what I'm going to do is I'm going to multiply the tangent of 15 by 57.3. .34 rather. What we get is 15.36. Okay, let me erase this. Y equals 15.36 t. Okay, so once again, you see that if we knew what t was, we could very easily solve for y. If we knew what y was, we could very easily solve for t. Okay, we don't know what either one of them are, but fortunately, we have two things that both equal y. You have two things that both equal the same variable, then they are, by definition, equal to one another. And so let's go down here. What we know then, as a fact, is that 40.15 t minus 4.9 t2 is equal to 15.36 t. Okay. And so we don't get confused, let me draw a little squiggly line here, just kind of separating some of our work. Okay. So now that we have this little setup, right, we can solve for t. Okay. So the first thing that I would probably want to do is just move this to this side and move this to this side. These are like terms, 15.36t and 40.15t, right? They are like terms, okay? So we can subtract this from this side. We can add this to this side, and then we can go from there. So I'm going to subtract 15.36t both sides, okay? And I'm going to add 4.9 t squared, okay, both sides. Okay. And what I end up with, let's see, what's 40.15 minus 15.36. So 40.15 minus 15.36, okay, was 24.79. 79t, and that's going to be equal to, of course, 4.9 t squared, right? Okay. So you can kind of see where this is probably going, right? The next thing we can do is we can just divide both sides by t, right? If I divide both sides by t, I'm running out of room here a little bit. Let's see if I can draw down there. Okay. This cancels, right? If I divide this side by t, we just get t. This squared basically cancels, right? Because this is just t times t. If I divide it by t, right, one of those t's cancels out. So keep that in mind. We end up with this. 24.79 equals 4.9 t. Okay. And so, makes sense then. are 24.79 divided by 4.9. This is how many seconds this projectile, is going to be in the air, right, after we fire it, both the y and the x-axis, right? So 24.79 divided by 4.9, okay, it's about 5.06 seconds. So this isn't our final answer, but I'll circle it just because this is kind of a big deal. And this kind of breaks the problem a little bit, because now we have a value for t, and as you've seen up here, right, we've already solved for y, right, with respect to t. Right? We have multiple equations here that we can use to solve for y, and they should give you the same answer, right? If you get slightly different answers on this, it's probably due to rounding errors, which I may have committed myself, right, in the process of this. But you're not randomly going to get as close as a tenth, right, or a hundredth, right, from each other, right? That's not going to just accidentally happen. So it's good for students that solve problems like these to try and not round, right, as much as possible, but just for convenience sake here, right? I've done a little bit of rounding, but these should ideally give you basically the same answer. Okay, so let's go with the simpler one right here. Let's go with y equals 15.36 times t. Okay, so then y is going to equal 15.36, right, times 5.06 seconds. Calculator here. Okay, 15.36 times 5.06. So our y, right, is then comes to 77, about 77.7 meters. Okay. So just out of curiosity, right, to see if I had any kind of glaring rounding errors or made any mistakes, and this is like a good way to check yourself when you have these two equations that should equal the same thing, right? Let's see if y also equals this, or it gets reasonably close to it when we punch 5.06 into these t's. Okay, so 40.15 times 5.06, okay, minus 4.9 times 5.06 squared. And again, I get 77.7, okay? So I think we've done our work well, right? And we have this value for y, okay? This is 77.7 meters above the ground, okay? All we need now is x, because remember, once we have x, right, we already have y. Once we have x, we can just plug them into Pythagorean's theorem and we get a value for d, okay? So let me go here when we have more room, but let me just go back and so we can remind ourselves, right, that x is simply going to equal v naught x, which we have right here, multiplied by t, which we have right here. So v naught x is 57.34. X is going to equal 57.34, okay, multiplied by t, which is 5.06. Equal to 290. About 290 meters. So now, right, the only thing left to do is just calculate d. And we know that d is going to equal the square root of x squared plus y squared. We know that x squared 290. X rather is 290, right? So 290 squared plus, what was it? Y was 77.7. We will square that as well. Okay. And D will then equal, let's see, 290 squared plus 77.7 squared. And then we will take the square root of that entire thing. And D equals 300.2 meters. Final answer, this projectile, when launched at this initial velocity, this many degrees above the ground, right, or an incline this many degrees above the ground, and this many degrees above the incline, will travel 300 meters along this hill. And we're done. I hope this made sense to you, right? And yeah, thank you for watching.